Hello, calculus students, and welcome to another online lesson. Today, we're continuing our discussion of probability distributions, but we're going to be talking about a specific type of probability distribution known as a binomial distribution. So we'll be talking about what a binomial distribution is and how to identify such a thing. And then we'll be solving problems using both the binomial formula as well as our TI calculators. All right, to start off with, when there is a repetition of independent trials in which there are two possible results, success or failure, we have a binomial experiment. So when I say success and failure, that could be any number of things of, checking whether I actually pass or fail on a test, or it could be something as simple as showing up to school or not showing up to school. But again, where you have lights on, lights off, something happens, something doesn't happen. Faulty light switch, not faulty light switch, things of that nature, where there's a yes and a no response. That is a binomial distribution. How do you find the probability? We have this formula here, which I think looks a little different in your formula packet, and I will show you some ways we can change this to make it look more like our formula packet. But this is saying the probability of some variable when it equals some number that we're talking about, we find using this formula here. So you take n, which stands for the number of trials. R is the number that we want to have to be successful. We're using our choose notation that we showed last class, last video. Probability is the probability of the success or the thing actually happening that we're looking for, and we take that to the power of the number of times we want to be successful. Q is your probability of failure, or the complement of P, and that we take it to all of the remaining trials that there are, n minus r. Another way we could write that is the probability, again, for our variable equals some value r is equal to n choose r, using that notation there. Then you could have p again to the r, and then instead of writing q, you could just write complement of p, or 1 minus p to the power of n minus r. So I think that's probably closer to how it looks in your formula packet. So what does this really mean? Can we think of an example of where this can actually happen? Well, let's say that in a calculus test or calculus class, I have 40 students. And I know that the probability that a student will pass my exam is, let's say 80%. So P is equal to 0.80 or 80%. And I want to know what's the probability that I will have 35 students actually pass the exam. So what we would do here is, again, we know it's a binomial distribution because you've got the option of passing or failing. So if I had to set this up, I'll do it in blue. I would say, so the probability that the number of students, that's what big X stands for, the number of students passing my class is 35, is equal to the total number of students, so 40, choose 35, times the probability that a student will pass, because that's what I want to find out, 0.8, to the power of the number of students I want to have pass, which is 35. And then I do the complement of that, which would be 0.2, or 1 minus 0.8, to all the remaining. Well, I had 40 students. I want 35 to pass. That means there's 5 left over who do not. And this would give me the probability that I would have 35 of my 40 students pass. And that is an example of a binomial distribution. A couple other things to add here. as I just pointed out, we've got that there. The n could be, or the r could be replaced with an x. N choose x can also be written using that sort of matrix or vector-looking sort of notation there. Sometimes they'll talk about a bin notation where n is the number of trials essentially that we have, and p is the probability of success. And so that's a quick way to give that important information. You can even write that on an IB test. For all binomial distributions, we're talking about discrete data, meaning you can only have whole number responses. It's not continuous, it's not measured. There are two outcomes, again, we call success and failure usually. The trials are independent, so the probability of success for a particular trial is not affected by the success or failure of the previous trials. So just a few things to keep in mind. And as we do more of these, as you see more examples, this somewhat confusing slide will hopefully begin to make a little bit more sense. So to start off with, 72% of union members are in favor of a certain change to their conditions of employment. A random sample of 5 members is taken. Find the probability that 3 members are in favor of the change in conditions. So let's start there with part A. So first and foremost, how do we know this is a binomial distribution? Well, you've got two options. You're either in favor of the change or you're not in favor of the change. So success or failure is right there. We are sampling 5 members. We don't know how many members are actually in the union, but we are sampling 5 of them. And so that becomes our sort of number of trials, our n. So if I had to set this up to begin with for part A, we have 5 trials. Now we want to know what's the probability that 3 members are in favor of the change in conditions. Now from last class, we would know the expected value is not 3. 72% of 5 is not equal to 3. We want to know what's the probability that 3 are actually in favor. So we're going to do 5, choose 3. And then we do our probability of success. And again, we're talking about being in favor of it. So the probability of being in favor is 0.72. And we want to have 3 people have that success or be in favor. Then we talk about our failures. We can do the complement 1 minus 0.72 or 0.28. That's our probability of failure or not being in favor. And there are 2 left over. There were 5 total, 3 were in favor, so 5 minus 3 gives me 2. And that's my setup there, and then we can put this into our calculator. So I will show you how we can do that. We said that we were doing 5, choose 2, so 5, and then we go to math, and arrow over to probability, NCR, so we have 5, choose 3, times 0.72 to the power of 3, because there were 3 members that we wanted to have be in favor, and then times our probability of failure, which was 0.28, or the complement of our p, to the power of our remaining members, which would be 2, and we end up with a probability of 0.293. 0.293. And that would be an example of a binomial distribution using the formula. Now I'm going to set that aside, and for part B, it says, now find the probability that at least 3 members are in favor of the change conditions. So maybe they needed to make a vote in that subcommittee and they needed a majority, so they want to make sure that there's at least 3 members. Well, 3 members could be 3, it could be 4, or it could be 5. Any of those things would be at least 3. We already know the probability of 3, so we still need to find the probability of 4. So what we would be doing really is, for part B, the probability that x is greater than or equal to 3 is what we're finding. And that would be equal to the probability that x equals 3, which we already figured out, plus the probability that x equals 4, plus the probability that big X equals 5. So what do I need to do? On the calculator, I'm going to add on, I'm just putting plus, so that takes my previous answer, plus I'm going to do 5 choose. Actually, I bet there's an easy way to do this. Let's try this. I'm going to press second, and I'm going to press enter, which brings everything else down that I just did. And that's not exactly what I want to do, but we can make it work this way. So that takes my previous one, brings it down, and I've got 5 choose 4 this time. Change all my 3s to 4s. And then there's one more thing that I need to change, which would be my power of 2, which is now to the power of 1. So I can press enter again, and so I find the probability of having 4 members in favor is 37.6%. And I'm going to do it one more time, and this time to the power, I'll do 5 choose 5, which I already know is 1 in my head, and then I have 72% to the 5th power, and this one's going to be to the 0 power, which essentially cancels it out or makes it 1. I can do that. I get that value. Now, what do I need to do? I need to take all 3 of those answers, add them together. So this time, I'll take that answer, so I don't have to type in the last one, and just add the other 2 on. I'm going to not round to 3 significant figures here. I'm going to go to maybe 4 or 5 so that I get a more accurate answer. So I'll take that original probability we had, which was 0.29262, should be good enough. I could go 63 to round properly, plus my second answer, the probability of choosing 4 members in favor, which was 0.37262. I'm sorry, 3. And that's good enough, really, right there. I've got my 5 significance, and I press enter. So I'm looking at about 86.2% is the probability. And again, that was the probability that x was greater than or equal to 3. All right, so that's a binomial distribution using the formula. Now, on the next slide, there we go. We're going to do this again. This time with technology. Now you say, didn't you just scroll down with your calculator, Mr. Peacock? You already used technology. And yes, I did, but I was using the formula, and the only thing I was using the technology for was to help me do exponents and my choose notation and stuff like that. Now what I'm going to do is show you how we can get these in a much faster way. So 3 members are in favor of the change in conditions. Going back to part A, we already know our answer is 29.3%. But we're going to find that much faster. We're going to go to our distribution menu, which is second, and then the vars key, and you'll see DISTR written above it. So second key, and then the vars key, and again, that vars key is right to the left, or just below to the left of the down arrow. Now I am going to use the cursor and arrow down until I get to something that says binom PDF. Choice 0, binom PDF. I'm going to press enter here. If you have the updated operating system, it'll tell you what you want. But the first thing we put in, just like we would in the formula, is our number of trials. After that, we put in our probability of success, which in this case is 0.72. Again, separated by a comma. And last but not least, we put in the specific trial or the specific outcome that we want, which for part A was 3. So you need 3 numbers. Once again, the number of trials, the probability of success, and then your R value, or the number of trials that you want to have success. The ones that you're choosing. And we press enter, and voila, we have our answer of 29.3%, or 0.293. A lot faster, a lot easier. You should know how to use both of these, both the formula and the calculator formula. Now the next one says at least 3 members, and you say, oh, well, this is going to be great. We'll take that answer, add it on to 2 more, and we can do it that way. So I'm going to take that previous answer plus, and now this hopefully will work out for me. So I do the binom PDF again. Yep, so I have my previous answer plus binom PDF 5, comma, 0.72, comma, the number of trials I want to be successful in this case is 4, plus, and we'll do one more of them, binom PDF, 5 trials, probability of success 0.72, and then the number that I want to have success, which is all 5 now. So I had originally my 3, then I'm adding on 5 choose 4, and now 5 choose 5, and I am left with 86.2%, which is the same value we got from before. And that seemed pretty fast, but we can do it even faster. There's another function on the calculator known as binom CDF. Binom CDF, the C stands for cumulative, meaning adding up. And so I'm going to select that. You start off the same way. We have our 5 trials, and we have our probability of success, which is 0.72. But last but not least, our value is not the value that you want. It's the value you want plus all others below it. So if I put a 3 in now, I won't get the probability of 3 members being in favor. I'll get the probability of 3 members being in favor, plus 2 members being in favor, plus 1 member being in favor, plus no members being in favor. So all of those probabilities added together. Well, that's not exactly what I want for part B. For part B, I want at least 3 members, which means I want 3 members or 4 members or 5 members. The calculator doesn't work that way. It always does this number and below. So I'm going to put in a 2. Now think about it. Why did I put in a 2? What is that going to give me? That's going to give me the probability of 0 members, 1 member, 2 member being in favor. 0, 1, and 2. And yet for part B, I wanted 3 members, which is at least 3 members, which is 3, 4, and 5. So what I've done is I've selected the ones that I don't want. The 0, the 1, and the 2. If I press enter, I'm not going to get the right answer. I'm going to get the complement of the right answer. How do I turn it into the right answer? I subtract. 1 minus that answer should leave me with my right answer, which is 0.862. That's exactly what we had before. Or what's another way to do this? So if you know that you are trying to get above a value, pick the one below it, which again in this case would be 2, and start off by subtracting. So I can do 1 minus, go to my distribution. I'm worked backwards that way to get there faster. So binom CDF, again, 5 trials. The probability was 0.72, and I wanted to get rid of the 2, the 1, and the 0. So I put a 2 in there, which is my highest value that I'm getting rid of. I press enter, and again, there's my right answer. So, ladies and gentlemen, that is our probability distributions. For this last one, how could I notate the work that I'm doing? Obviously, we can't just say that I'm doing binom CDF and stuff like that on the calculator on an IB test. But what would be acceptable is to say the probability of having x greater than or equal to 3 is equal to 1 minus the probability of x is less than or equal to 2. And that's essentially what we're doing on the calculator, and that would be an appropriate setup to the problem showing work. A few practice problems for you on page 623. Again, our goal for today was to be able to define what a binomial distribution is. Again, these are probability problems involving success and failure, 2 different outcomes that we're looking for, repeated numerous times. We wanted to be able to solve it using our formula and with technology, which we did. And then again, hopefully we're going to be able to use this to solve IB problems as well as the problems here in the book successfully.